Hello, this lesson here is going to be about mathematical functions. So the basic question we're going to answer is, what is a function? And so a function is something you hear and see about a lot in mathematics, and many people have different impressions of what functions are. So the first thing I want to show you, just a variety of different types of things that people tend to think of or classify as functions. So you can see on this slide here, you think about formulas, right? People think a lot about functional formulas like y equals the sine squared of x. Also, in terms of functions, we tend to think of graphs. So you can see the graph over there on the right. And then also in statistics, when we think about data, you can fit a function to the data, and then you can describe any trends in the data. And then as we get more advanced into engineering problems, you think about things like a surface or other things that we see in statistics. So these are the general things that we think of when we think about mathematical functions. But what I want to do here is to talk about the precise mathematical definition of a function. And even though it's really sort of a difficult thing to understand, what we're going to see is that this is a pretty common thing found in everyday life. So the next slide I'm going to show, this is the scary one, the mathematical definition of a function. So I'm going to read this here. This says, a function is a correspondence between two sets such that for each element in the first set, there is precisely one element, a corresponding element in the second set. So I'm going to give a diagram of this. Now, the first time we see something like this, we tend to think just nonsense. Like, what does this definition mean? So I'm going to get a little mathematical on you here, but this is the basic idea. And so we have two sets. One of them here we tend to call the domain, and this one here is the range. So when we look back at that definition, it says we take an element in one set, and then there's a corresponding element in the other set. So in the domain, you could say we have like an element there, something like x, and then we have a corresponding element in the range over here at this point. And typically, mathematicians like to name things. So this function, we might call it f, right? So then we have x in the domain, and then this element here we would call f of x. So we would call the function f of x, and we might write it down this way. So that's how we think of the idea of symbolically what a function is. But this is really the definition showing you that a function is nothing more than a mapping. So you have an element in one set, and it takes you over to a different element in the second set. So what I want to do here is really kind of make this definition a little bit closer to you, so that way you can start to understand exactly what it means. So I want to show you guys a couple of examples of everyday functions. So these are things that we see on a daily basis. You might not even think of them as mathematical functions, but they really are. And here's the first one I want to show you guys. And it's surprising, but a vending machine. So when you think about walking up to a vending machine and just buying something, whether it's a bag of chips or a refreshing drink, this is one of the simplest examples of a mathematical function. So what I'll do here is show you how you can think about this. So when we think of a vending machine, right, this is the corresponding two sets here. So you have an input, and you also have an output. So we typically think of this. Your input is the money, right? That's the money that you put into the machine. And the output, of course, is your expectation of what comes out. So this is the soda, or as I have learned, pop, as they call it in the Midwest, right? So this is the idea where you can see it's a direct mapping that for one corresponding element here, your money, you expect a corresponding element from the machine, right? Mainly the pop that comes out. Now, ways of really understanding a function is to play around with that mathematical definition just a little bit, and you can see that those situations are unnatural. So I'll give you an example. What if you put your money into the machine, and lo and behold, this has happened to all of us, nothing comes out, right? So this here is a bizarre situation where there has been an input, but maybe the soda will get stuck in the machine, or maybe the machine is out and it took your money. This is not good. So we wouldn't consider this to be that mathematical function idea. And then this happened to me in school once. I don't know if it's ever happened to you. You put money into the machine, and then this might happen. And I swear to you, it did happen once. Right? So you put your money in the machine, and 2 sodas come out. Right? So you get both a Sprite and a Coke. So even though these bottom situations, right, we would consider them abnormal and strange, they could happen, but they don't correspond to the definition of a mathematical function. So if we go back, I'm going to go back to that definition, right? It says there's a correspondence between the 2 sets. For each element in the first set, there is precisely 1 element in the second set. So you can see not getting a soda or getting more than 1 soda, that is not the situation that adheres to that definition of a mathematical function. Now, one thing that is interesting to think about is this could happen. So I'll sketch another diagram here where we have the money and the soda that comes out. So someone might walk up to the machine and purchase a Sprite, for example. Right? So that person makes that exchange and gets a soda. It could be that a second person will walk up to the machine and purchase the same drink. So really we're saying that 2 different inputs could lead to the same output. And that is an okay situation as long as you have the 2 different sodas. So this situation is very similar to this one here on the bottom, but you can see this here fits the definition of a mathematical function. This one here does not. All right, so one more example I want to show you guys, different than a vending machine. And so I just pulled this data last night. These are the parking rates at Midway Airport. So I don't know if these are actually current, depends on if they update their page. But we rarely think of parking our car and think about mathematical functions in that same thought. So what I'll do here is I would like to graph this data, because then that way you can go back to that definition and make sure that you can see that this is actually meeting the same requirements of that definition. So this is telling us here for the first 10 minutes are free. So I'm going to try to graph this here, do a decent job of it. So we have time on one axis, and then we're going to have the fee over here, and I should look at the units. So based on this graph, they're using minutes and hours. So I'm going to go with hours there, and we have dollars. So I'm not going to graph the whole table, but maybe just the first 3 hours or so, something like that. So I will do 1, 2, 3, like that. And then the rates go up to around $8. So I'll mark that at 8, maybe find the halfway point, something like that. So what I'll do is I'll plot the data, and then we'll go back to that definition. So luckily it says here for 10 minutes it's free. So this means if you enter the garage, I'm going to have to estimate here. So 10 minutes, this would be 1/6, right, of the hour. So I'll call it something like that, right? So if you stay in the garage for a short period of time, you don't have to pay. So you can see your fee is nothing there. But then 10 minutes to a half an hour, they charge you $2. So a half an hour, right around here. And so $2 would put us right here. So it almost looks like a set of stairs, right? That's what's happening here. And then 30 minutes to an hour, this is where they make their money, right? They go up to $5. So that is up here above 4. And this is all happening in the first hour. So that's really a graph, right, of what it looks like. And then maybe I'll do one more line here. So it says 2 hours or less would be $6. So I'm going to jump up here. just like that. And then, of course, the graph will continue on, right? You could plot some more of it. So if you look at this graph, it looks a little strange. It's definitely discontinuous. But again, I'm going to go back to that definition just so that we can see that this is actually a very practical type of thing. So it says any element that you take in the first set, there's one and only one element that corresponds to it in the second set. So if you look at that here, this is our first set, right? Our input is the time. This is something that we have freedom over. We can spend as long as we want in the garage. And then the output is the fee, right? That's what we actually have to pay. So there's no way that if you enter the garage, the people running the garage are going to ask you to pay 2 fees. They're going to say one and only one fee, and it's going to be based entirely on this graph. So if you look at the graph here, you could say, suppose you spent 90 minutes, right, in the garage, so maybe 1.5 hours. So you'd have to find that input and look up to the graph, and you can locate the spot here, and you can see right here, you'd have to pay $6 for that. So even in the tricky areas, like exactly 1 hour, you can look at the graph very carefully, and you can see that they will let you get out of the garage by paying $5. But as soon as you spend slightly more than 1 hour in the garage, then they're going to bump that up to $6. So basically, the point of this lesson is, as abstract and strange, right, as this definition appears, this is a very practical type of thing that you can find even when you think about parking your car or just buying something here in a vending machine. Thanks.